Okay, hello, welcome to my 10th and final video of this series where I will cover electrochemical plating, chemical mechanical polishing as well as low-K dielectrics. So let's go straight into the content today. So the main principle that that keeps appearing in this video is the idea of replacing our interconnect metals from what was previously aluminum to a copper based system, and that is the reason why we need features such as chemical mechanical polishing, which we'll see later. So previously the interconnects that were present in a semiconductor wafer were predominantly made out of aluminum. However, there were certain problems with this system of aluminum interconnects that was encountered that actually drove the change to a copper-based system. And so one of the problems was this idea of stress migration. So when aluminum was actually used as an interconnect metal, we observe things like Hillock growth that you can see on this diagram on the left over here. And this is because of the low melting temperature of aluminum and therefore its relative ease of deformation. So aluminum is a relatively low melting point metal and therefore can be easily deformed, especially when processes are being performed on it at elevated temperatures. In addition, there's also a pretty large difference in the thermal expansion coefficient between aluminum and that of silicon, as well as the other materials that are present in the semiconductor wafer. And so this mismatch of thermal expansion coefficients can cause distortions in the volume and geometry of the aluminum interconnects, and this is especially the case because oftentimes a deposition of the metal is conducted at a different temperature compared to device operation, right? So the metal is often deposited at a higher temperature, or anneal is conducted at a higher temperature than your room temperature when your device is operating at. And a second also very important problem is this idea of electromigration. So when there's a current flowing in aluminum, or basically any metal, okay, so this example on this diagram on the right shows copper, but it's the same for aluminum. When the current flows through the metal, right, electrons are moving, and so there's something called like electron wind. And so these electrons, when they move under the influence of the electric field, they impinge upon and bombard the metal ions, right? The metal atoms or ions in the lattice structure of the metal, and so this creates a kind of momentum transfer to the metal atoms, causing the metal atoms to undergo a drift, right, in the direction of the conventional current. Sorry, in the direction opposite to the conventional current, because it's in the same direction as the electron wind. Okay, so this will cause a movement, or you can call it a diffusion, basically a motion of these metal atoms, right, in a certain direction, and we call this electromigration because it involves the migration of the metal atoms under the influence of the electric current. So what then drives the replacement of aluminum with copper is the fact that copper has a lower resistivity. So that in itself is a good thing because it basically reduces the delay in the transfer of, let's say, signals in your circuit. It also reduces the amount of loss of electrical energy to heat and all that kind of thing. And in addition, very importantly, it also has a higher resistance to electromigration and stress migration. And specifically, its higher resistance to electromigration means that we can operate the device at higher current densities while still keeping electromigration to a much lower level compared to the use of aluminum interconnects. Okay. So there's a difference between aluminum and copper patterning schemes. So when we shift from aluminum-based interconnect system to a copper-based interconnect system, there's a difference in the way that we have to pattern this metal features. So let's take a look at the left-hand side. Let's assume this is aluminum. Let's say for aluminum patterning, we can basically deposit a uniform layer of aluminum, for example, through evaporation. And then after that, right, use lithography and subsequently etching, right, in a plasma etching to define where you want your aluminum features to be, like to define the shape and the location of your aluminum features. However, for copper, the scheme is slightly different. The scheme is that we have to deposit a seed layer and plate copper into the gaps before polishing the excess copper down. And so in this way, we get the copper into the gaps, and it is the gaps in the layer, right, in the layer below. So maybe this is like can be an oxide layer, some dielectric layer. It's the gaps in the dielectric layer that defines where your copper goes into. So this is obviously different scheme compared to aluminum based patterning, which is similar to your dielectric based patterning. It's an etching based mechanism, whereas in this case for copper we do something, this is actually called a Damascene process. Okay, so why do we need a Damascene process for copper? So this is actually simply because copper does not have any suitable etch chemistries. So whereas if you see for aluminum, if we use a chlorine based or bromine based etchant gas in the plasma chamber, we can actually produce our byproducts of the etching to be things like aluminum chloride and aluminum bromide. And these are actually relatively volatile gases at the temperature of the plasma chamber operation. So these gases can then be diffused away, and so therefore successfully removing your aluminum from the wafer surface entirely. However, if you use copper as your metal, copper, fluoride, chloride and bromide are all have very high boiling points, and so they are not a volatile gas. So that means that even if you use a halide based etching gas, the resultant etching byproducts is not volatile and cannot be readily removed from the wafer. And that is why copper cannot be easily etched away, because the byproducts will still stay on the wafer, very difficult to remove and cause contamination. So copper is not easily etched, or you can say it cannot be cleanly etched by a dry etching mechanism. And so when we actually deal with interconnects, right, you'll see the term via and trench being used very frequently. So what is the difference between via and trench? Sometimes you may see 2D diagrams of via and trench. For example, you see like this, right, via and trench, but from the two-dimensional picture it's not very easily to visualize what is going on. So we need a three-dimensional picture like this. The trench is for you to lay your metal line. So you dig a trench, so you can think of it as a long line, and that is your metal line that connects the various devices in your chip, right? The various devices, you can think of it, the various MOSFETs in your chip. And via is a straight line downwards to connect your line, your metal line, with the device itself that is below it. So that is the idea of a via and trench. So you etch your via to fill it up, to connect to your device or connect between two metal lines, and you etch a trench and you fill in a metal line into your trench, right, to act as the interconnects locally between the devices or globally between different like subsections of your chip. Okay, so therefore, right, because we have both etching of via and etching of trench, and deposition in your via and deposition in your trench, we have a dual Damascene process. So it's basically the same as a Damascene process, where your Damascene process refers to filling in a single like trench or via, but now that we have both a via and trench, we call it a dual Damascene process. So an example of a self-aligned via trench etching is shown here, where you first have a hard mask, you etch your hard mask, then you put a photoresist, and then you etch down a certain amount. So this width of this first dielectric that etching is the width of your via, and then your second etch means that your second dielectric will now be etched downwards with the dimension of your via. But now, right, your first dielectric layer is etched based on the dimension of the hard mask, which is the dimension of the trench. And so therefore in basically the second etch step, we get to open up both the via and the trench simultaneously, and these two are aligned in the sense by this single etching step. So we call this a self-aligned via and trench etching. So once we successfully conduct the self-aligned via and trench etching, we can lay down the barrier layer and the copper seed and then electroplate. So why do we need the barrier layer? The barrier layer is often conductive nitride, such as titanium nitride or tantalum nitride. So the reason why we need the barrier is because copper has a pretty high solubility and mobility in silicon. So we do not want our copper atoms diffusing into your dielectric and then diffusing into silicon and then altering the electrical properties of your silicon semiconductor. That is highly undesirable. So you need a barrier layer to prevent this kind of interdiffusion from happening. And then a seed layer is needed for the electroplating process later. Because if you think about it, electroplating requires a conductive electrode to be plated. So you need to have a seed layer to make sure the electrode is conductive. But not only that, it's also to ensure that deposition can occur more uniformly to achieve grain size control and things like that. So eventually, it's that your metal is electroplated into your via and your trench, and eventually the surface is also planarized through a chemical mechanical polishing step. Okay, so however, in addition to this self-aligned trench method, right, there may be some issues with the self-alignment. So there's also other kind of via trench etching method that's widely done. The first is via first method. So we etch down the via first, and then you plug up the via, you fill up the via with something like a plug before you etch your trench. And then after you remove the plug, your via plug, and then you have your opened up via and trench that's ready for your plating of your copper or whatever interconnect method that you are going to use. Okay. And another method, of course, you can do via first, you can also do trench first, right? So the idea for trench first method is that you etch your trench first, then you actually fill up a part of your trench, right, with photoresist, such that only the dimension of your via is exposed, and then you etch down your via. Okay. However, there's a problem with this trench first etching, and that is that you see your photoresist here has a non-uniform thickness. But remember, right, when you learn in photolithography topic, right, that your photolithography exposure machine has a certain depth of focus, a certain depth of field. So if your depth of focus, right, is very small, and then your resist in this case now has a large thickness non-uniformities, right, it will result in the poor resultant resolution of pattern definement in your photoresist. So that is a big problem for the trench first method, and yeah, so that is one of the problem of this method. And so now we will cover the basics of electrochemical plating. I won't cover too much because most of you would have learned this in your secondary school already, the idea of your electrochemical plating cell, right? So it's a very simple principle actually. So your anode, right, dissolves, which is assuming to be copper, it dissolves away, right, and your copper is then plated onto the cathode, and this is because of your there being an EMF source, right, that supplies electrons to your cathode, where that allows your Cu2 plus, right, ions to be reduced to copper metal at your cathode, whereas at your anode is the oxidation reaction that's happening from copper metal to your copper 2 plus ions. And your electrolyte, right, must be an ionically conductive electrolyte. So normally it is copper salt, aqueous copper salt, right, to provide the higher concentration of copper ions for the plating to occur on your cathode. And oftentimes it's also modified with other kind of ionic species. Sometimes it's an acidic species like like hydrochloric acid or maybe sulfuric acid, right? This helps to basically maintain a certain pH of your solution that may be desirable for certain properties, as well as, you know, increasing the ionic conductivity of your electrolyte. And why do you want to increase your ionic conductivity of electrolyte? That because that reduces the internal resistance of your electrochemical cell, that allows for more efficient, energy efficient plating to occur. So yeah, actually a lot can be discussed of electrochemical plating, but I will not discuss the very nitty-gritty details in this video. So but compared to, let's say, just plating a jewelry, for plating a jewelry we just want a uniform coating around the ring or around the whatever jewelry that you are plating. But in the case for electrochemical plating for the interconnects in the semiconductor wafer, note that we are filling trenches and we are filling vias. So these trenches and vias can be very high aspect ratio features. So this means that the electroplating step must be able to fill these high aspect ratio vias and these high aspect ratio trenches without leaving voids in between. Okay? So it generally requires that this process is better than conformal, because when there's a conformal or sub-conformal plating, you tend to leave seams and voids in the middle of the via and trenches. However, if you use a super conformal, also known as super filling, right, kind of recipe that's able to achieve that, we can obtain a defect-free filling of the high aspect ratio trench and vias. So to achieve that, right, we generally modify the electrolyte by adding small concentration of chemicals known as accelerators, suppressors, and levelers in very small concentrations to allow the right profile of electrochemical plating. So let's take a look at what these are and how they work. Okay, so normally in your electrolyte, the basis of your electrolyte is still sulfate, copper 2 sulfate salt, and it's also modified with sulfuric acid to achieve the right pH for, especially for your other chemicals to be able to exert the desired effect. So, and the organic additives is the accelerator, suppressor, and levelers that we talk about. So what are the accelerators? The accelerators are smaller charged molecules. So as you can see, they have this kind of like sulfate kind of group, and so they are negatively charged. And so you can imagine that your wafer is also an electrode, right? So it is also charged, correct? As you can see over here, your electrode is also charged. So so it's able to actually attract your this charged species, your charged accelerator molecules, that is able to enter into the trench, right? Because these molecules are small in size, right? They are not that big. Versus you see the other organic molecules, they are much bigger, right? They are like polymeric kind of molecules, or with very large, bulky aromatic groups. But over here, these molecules are rather small, so they are able to enter into the trench to accelerate the deposition at the bottom. So these molecules, because of their charged nature, they are able to, let's say, attract your copper ions, for example, to your wafer surface to accelerate the deposition that occurs at the base of the trench. And what about your inhibitors, also known as your suppressors, right? These, in comparison, are large uncharged polymeric kind of molecules. So they are large molecules that, because they are large, they cannot easily enter into your trench, and so they loiter around the surface of your wafer. And so because these molecules are large and they're also largely non-polar, so they are able to kind of block parts of your surface from the easy deposition of CO2 plus ions into copper metal. So in this case, what it does is that it reduces the deposition rate of copper at the top surface of the wafer. Okay? This is to allow the trench to fill up first before too much deposition occurs at the surface of your wafer. Right? Why is this so? This is because without the suppressor, deposition rate at the surface will occur at a much higher rate, because the diffusion of CO2 plus ions, of copper 2 ions, to your surface of the wafer is going to happen at a much faster rate than at the bottom of your trench. Because at the bottom of the trench, it's harder for mass transport to occur. Right? It's harder for mass transport to occur because the diffusion layer, you can think of the diffusion layer to be much thicker, to be more than the entire height of your trench. And so that's why we need these suppressors, right, to balance out the deposition rate, to allow deposition rate at the surface to be slower, such that the deposition rate in the trench and vias can catch up. Alright, and the leveler, we see the leveler is similar to the inhibitor. That is a large molecule, right? Not really as large as your inhibitors, but also fairly large and bulky. And the purpose of this is to ensure level deposition across the surface. Is to ensure that the deposition rate doesn't occur too fast at one spot and too slow at another. So often case, right, the right ratios and the right chemicals to be used for this is a trial and error kind of scheme, right? So it has to be determined experimentally what is the best ratio and best composition, right? Because it's obviously you can imagine that this is a very complex system to do any first principles modeling. Okay. And so now remember that we covered under the Damascene process that subsequent to our electrochemical plating, we need to have a polishing step to polish down the metal that is deposited on the surface of your wafer. Okay, so the way we do that is through this machine equipment called CMP, which is a chemical mechanical polishing machine. Sometimes you see them calling a chemical mechanical planarization machine, but it's the same idea because you're polishing down the wafer to ensure it is planar, so you can also call it planarization. So in this case, the wafer is actually pressed against a rotating pad, and so this rotating pad has a certain asperity that allows it to actually engage with the wafer surface. And at the same time, there's also a slurry that's applied to the wafer surface, and this slurry contains both chemicals that can chemically react with whatever you're polishing on your wafer surface, as well as abrasive particles. For example, certain hard materials like carbide carbide materials that are hard, that can actually help to mechanically scrub off material from your wafer surface. So basically there's the idea of the pad that presses against your wafer surface and the slurry that is supplied to your pad to polish out the wafer surface. So the parameters that process engineers need to tune in your CMP machine is things like the pressure of your pad, rotation rate of your pad, slurry flow rate of your slurry, the pH of your slurry, as well as its chemical composition and the kind of size and concentration of abrasive particles that you're putting in. So why is this called chemical mechanical polishing, right? It's because not only is there mechanical removal of your material through abrasion, but there's also a chemical reaction that often occurs that makes it easier for you to remove material off your wafer surface. For example, if we are removing a primarily oxide layer, we add KOH, right, potassium hydroxide, to a slurry, which reacts with SiO2 to form a silicate salt, and this silicate salt, hydrated silicate layer, is then easily removed by the abrasive because it has a certain solubility in the solution. Whereas for metal, CMP, right, normally we add certain kind of oxidizing agents in the slurry that oxidizes the metal to create the oxide, and the oxide layer can then be removed by a high pH solution by forming basically certain hydroxide complexes with the metal that can be more easily removed, for example. Yeah. And so how do we define our planarization properties, right? We have this idea called a degree of planarization that tells you how planar your surface is after the CMP process. So it's very simply 1 minus your final step height over your initial step height. So imagine if it's perfectly planarized, there's no steps at all after your planarization, so your final step height is 0. So then your degree of planarization by definition will be 1, which indicates a perfect planarization of your wafer surface. Okay. However, right, CMP can also result in non-uniformities. More specifically, right, there's two kind of non-uniformities. One is called dishing and one is called erosion. So dishing, it occurs here in the blue area, right, which is your metal area, right, where basically, especially if your pad is pad pressure is being applied in a way that's not suitable for the material, and in addition to unsuitable pad stiffness, right, it can result in your metal features having a downward kind of curvature after planarization. And the other feature that can occur, the non-uniformity, so it's undesirable feature, is erosion. So it is observed that areas where your metal patterns are very close to each other tends to erode faster than areas with fewer of this kind of patterns. And so therefore it can be because for a certain semiconductor wafer, there will be areas where your patterns are closer together and areas where your patterns are further away from each other. So you can see that the area where the patterns are closer to each other, we have a greater extent of material removal by the CMP process. So this is why sometimes we may want to have dummy patterns in certain parts of your wafer, where to make sure that that part of the wafer is not completely devoid of patterns, but there's some dummy patterns, right, metal lines that don't connect anything, but purely to allow for easier process integration. For example, to reduce non-uniformities in the CMP polishing step. And so, as mentioned earlier, things like wafer pressure can affect the CMP result. For example, if you issue too high of a pressure, right, you apply too high of a pressure, your pad and your wafer can be, in a sense, slightly distorted in its geometry, and it can also result in a delamination between your wafer surface and the surface of the layer that's laid on your wafer that you're trying to polish. Right. And the second kind of factor would be your pad stiffness. So if you have a very soft pad basically follows your geometry of your wafer surface. So it polishes along the topography, right, that already exists. So you can think of the degree of planarization to be less powerful for this case. However, if you have a stiff or a hard pad, right, it bridges across the topography and basically it tints the surfaces that are raised, right, at a higher rate than the surfaces that are at the valleys, for example. And so this will result in greater planarization of your wafer surface eventually. Okay. So now I'll briefly cover the whole idea of your back end of line structure. So as you can see, the back end of line structure is a very complex kind of configuration as well, where you have many of your metal layers, and each metal layer, right, is connects different parts of the chip. So maybe the first layer connects the individual devices, then after that your upper layers connect between various regions in the chip that perform slightly different functions, like maybe memory, computation, things like that. And your eventual metal layer at the top, right, needs to connect with uh, whatever like bumps that may be deposited at the back of your chip, right, to connect with the greater system out there. For example, the motherboard of your computer, or the motherboard of your handphone, right? So it needs to connect with the outside world as well. Basically, that's what I'm trying to say. So basically, as your chip becomes more and more complex, the functionality becomes more and more complex, the features become more and more advanced, we see that there's an increasing number of interconnect levels that's required to form these more complex circuits. And so it then becomes more imperative to reduce the resistance of the metal wires, as well as decreasing the parasitic capacitance between your metal lines. And so what do I mean by this? Let's take a look at this diagram over here. Right, so we can consider the resistance of the metal line to be expressed by this formula, which I believe is very familiar to most of you that have taken physics in your secondary school days, right? It's your resistance is rho L over cross-sectional area. And in addition to that, we also cannot ignore the two capacitance contributions, right? One by the dielectric between the wires, and one by the dielectric between the wire and the silicon base below. And so we can add up these two capacitive components. And so, right, by using a Kirchhoff's current law, right, that indicates that the current through the resistor, right, so it's your potential difference divided by your resistance of a resistor is equals to the capacitance times your dV dt, right, which is equivalent to the current through the capacitor, right. We can actually obtain an expression of the output voltage of this system, right. And so we realize that this output voltage slowly turns on, so it has a kind of exponential kind of decay by increase, right, kind of feature. And so we observe that there's this term tau over here that's equivalent to your resistance of your wire times your capacitance of your stray capacitance, L over here and the CS over here. Right. So it turns out that as your RC constant, your time constant, also known as your RC constant, becomes bigger, your output voltage takes longer to reach its target level. It takes longer to reach its target level. And so therefore what we want to do is we want to reduce the magnitude of our RC constant to ensure that the output voltage turns on as fast as possible. So therefore, by looking at your expression for tau and your R and your C, we see that we can do this by doing two things: by reducing the resistivity of your metal wires, for example, by changing aluminum, your interconnects, into copper interconnects, right, that will reduce the resistivity of your interconnects. Or secondly, right, by reducing the dielectric constant K of your dielectric materials. So that is why we also need low K dielectrics. We need dielectrics that have a low dielectric constant to reduce the stray capacitance present between your interconnects, therefore reducing your time constant of turning on your device. And so how do we achieve a low K dielectrics? So the dielectric constant of a material can be decreased by two ways. So remember that the dielectric kind of behavior of a material arises from the polarization of the chemical bonds present in a dielectric material. So it then logically follows that if we have a decreased polarizability of the chemical bonds in a dielectric material, we can achieve a lower dielectric constant value. And so we can use less polarizable bonds, right? For example, your non-polar bonds like CC and CH are less polarizable. However, right, so there's a slight incorrect labeling in this diagram, because you may say that your silicon fluorine bond is quite polar, right? because your fluorine is a pretty electronegative element. However, you realize that the silicon fluorine bond is not so polarizable due to the small electron cloud of your fluorine atom. So even though it has a large dipole moment, it does not have very high polarizability as well. So these are certain bonds that we can use in our dielectric material, right, to replace your silicon oxygen bonds, for example, in your SiO2. And the second way is to simply decrease the density, have more pores in your material that are filled up with air, because air has a very low dielectric constant, right? So we can have a constitutive porosity. That means the material is in such a way that there's a low density and high porosity. For example, we may have a polymer chain that has a very large free volume, right? There's a very large free volume. A polymer chain that is very bulky, has many side groups, that in itself, right, it forms into a very low crystallinity, low density material. So that is constitutive porosity. There's also the idea of subtractive porosity, that we somehow remove material such to create pores kind of artificially in the material, right, which is also pretty hard to achieve, but it can also theoretically be done. And so therefore, right, we can achieve our low-K dielectrics through these two main methods. So these are some examples of the low-K dielectrics that have been used or have been proposed to be used in the semiconductor materials, right? For example, there's a silica base, so it's trying to not deviate too much from the idea of SiO2, but maybe incorporating some fluorine, right? So this is your fluorosilicate glass, right? Incorporating some carbon, right? Some carbon groups in. So this is like kind of your organosilicate glass, right? There's also the idea of using polymers, because that's what I said earlier, if a polymer chain is like bulky, right, and has many bulky side groups, then by right you can achieve a very good constitutive porosity, right, and therefore a low density, low dielectric constant material, right, polyamide, Teflon and all that, right. There's also the idea of using amorphous carbon, right, perhaps doped with certain amount of fluorine, right, and even, right, just leaving air gaps, right. However, there's a problem, because if there's too many air gaps, right, it affects the mechanical strength, right, the mechanical integrity of your material. Right, so there are certain considerations as for what low-K dielectrics we can actually use in our device. So the first one is that fundamentally your dielectric layer exists as an electrically isolating layer. Its main function is to electrically isolate your metal interconnect. So it needs to have a high breakdown field and a low leakage current. Right? And in addition, right, it also shouldn't absorb water. So it should have a high hydrophobicity and should not be hygroscopic at all, because when water is adsorbed, right, the OH bonds in water greatly increases the dielectric constant of the material due to the high polarizability of your OH bonds. Yeah. In addition, right, we also need mechanical stability of your material, because remember your back end of line dielectric materials often need to go through very aggressive damascene and mechanical polishing processes. So these require a certain mechanical stability and strength of the material. In addition, it also needs to be thermally stable. Your polymer, for example, should not have too low a glass transition temperature or too low decomposition temperature, because our back end processing temperatures can also be elevated as well. It also needs to be chemically and physically stable to processes like plasma etching, cleaning, lithography. It mustn't degrade, right, for example, under UV exposure in the lithography step, or it mustn't be too easily reacting with, let's say, your plasma cleaning steps as well. And it also must be compatible with the material that is being layered on and the material that is being laid upon it, right? So it needs to have similar thermal expansion coefficients with the other materials connected to it. It needs to have good barrier properties, right? That means there's not too much interdiffusion between the layers through your low-K dielectrics. As well as adhesion, right? The layers that you deposit on it must be able to adhere well to it, that there's no delamination or separation that can occur, right? And so basically there's also an idea where we can actually use a stronger material for processing, and then that material is replaced by a lower K material, or let's say that material is made to be more porous, right, through certain form of maybe selective removal of your material. That's also another strategy. So we process the wafer with a stronger material before replacing it with a lower K material subsequently. But of course, this is easy to say on paper but difficult to implement in practice. Okay, and so this actually marks the end of this video, and in the next series actually I will cover materials characterization for semiconductor devices when this series is fully developed. Okay, I hope I'll get sufficient time to cover this series, because I'm actually quite excited to share this kind of very interesting information with all of you. So it will be basically a follow-up series to this series, which has just ended. This is materials engineering, and because whenever you engineer a device, you need to figure out whether you did it the right way, and the way to figure out whether you did it correctly or did it well or how to improve it is through characterization, right? And so I will cover basically electrical characterization, optical based characterization techniques, electron microscopy techniques, atomic force microscopy, elemental characterization techniques, as well as vibrational spectroscopy techniques. So I hope that all of you who enjoyed this particular video can also follow me to watch the subsequent series. Okay, thank you, and see you in the next series.